In April 1974, this flare announced the successful 8-mile extension of a gas field in the Canadian Arctic Islands. Not an unusual occurrence, except for the fact that just a few feet below, for the first time, a 500-ton conventional land rig had been used to drill an offshore gas well using ocean ice as the rig platform. It has been estimated that the Canadian Arctic archipelago contains potential energy reserves of 35 billion barrels of oil and 200 trillion cubic feet of natural gas. With the discovery to date of 6 major gas fields on its islands, this potential is just beginning to be realized. Only 1/3 of the archipelago, however, is land, 2/3 being overlain by the Arctic Ocean and icebound 10 or 11 months of the year. It has been found that most of the discovered fields extend offshore, and many other good prospects to find by seismic crews working on the sea ice lie completely offshore. Engineering a method by which existing fields could be extended and new offshore fields discovered was therefore the challenge facing Panarctic Oils Limited. In meeting this challenge with Hecla N52, Panarctic, in its 7th year of operations, opened up a new chapter in high Arctic exploration. Natural sea ice, 6 to 8 feet thick, had aided the company throughout its operating history, providing safe landing strips for the huge 75-ton Hercules aircraft and roads for large trucks hauling heavy rig sections between islands. This led engineers to consider the possibility of drilling from the ice. Before this could be done, there were many complications to be resolved, including horizontal and vertical ice movement, the guiding of casing and drill string into the seabed, and most important, fail-safe well control. 3 years were spent gathering data on ice movement. Within a reasonable distance from shore, the horizontal movement was found to fall within the required limit, namely 5% of water depth over the drilling period. Panarctic was ready to turn theory into practice. In the spring of 1973, a 150-ton stratigraphic drilling rig and camp were moved offshore. The natural ocean ice, 6 to 8 feet thick, easily supported the rig, and 4 1,500-foot test holes were drilled. Water depth ranged between 137 and 290 feet, and the distance from shore varied from 1 to 3.5 miles. These tests were drilled at Christopher Bay, Elf Ringness Island. Having established the feasibility of drilling offshore with a stratigraphic rig, the next step was to move a conventional land rig onto the ocean ice. The information previously compiled was studied and evaluated. Panarctic's project engineer and drilling foreman met with the company's consultants, Westburn Engineering and Foundation of Canada Engineering, to draw up detailed plans. Several hundred miles southwest of Christopher Bay lay the Hecla gas field on Melville Island. The eastern flank of this field had been delineated by 3 onshore wells. Now, Hecla N52 would attempt to extend the field limits westward and prove the practicality of winter drilling from an ice platform. The well location, 8 miles offshore in Hecla and Griper Bay, was chosen in October 1973. In their search for this site, Panarctic's engineers and surveyors carefully traversed the 1-foot-thick first-year ice in a light-tracked vehicle. They were looking for a large pan of multi-year ice, which would be 4 to 5 feet thick and as close as possible to the seismic control. This would provide the base on which ice could be built up to the thickness required to support the conventional land rig. This thickening was to be achieved by progressive daily flooding in a program designed by Foundation of Canada Engineering. A start was made in November 1973. Flooding and freezing was done in layers of 1 to 2 inches at a time, depending on weather conditions. 30 below with a 5-mile-an-hour wind was considered ideal for rapid ice buildup. At times, while the pumps sprayed the platform with seawater, the temperature dropped to 50 below. Standing in the middle of the 400-foot diameter platform was a 6 by 9-foot cribbing, which would ultimately become the moon pool, the opening in the ice platform through which the well would be drilled. As flooding continued, progress was discussed at the Hecla camp, a quarter of a mile away.
Can you tell us how you progress in here now? How much ice have you got? How long did it take you to pump that 360,000?
Pumping 80,000 gallons an hour with 2 pumps. So we're gonna have to slow down a little, I think, today because our ice temperature is getting a little too warm. We should still be able to maintain our 3 inches per day progress.
The program was constantly monitored to provide data for present and future use. A portable seismic drill was employed to check the ice thickness. Daily measurements were taken of ice temperature, strength, salinity, and deflection of the original ice sheet under the weight of new ice. 2 months of flooding, averaging 2.4 inches daily, eventually brought the ice to a 16-foot thickness at the moon pool. By flooding from the center of the platform, the buildup of new ice gradually tapered down to meet the 6-foot thick natural ice at the edges, with the original ice pan bending under the weight of the new layers. By early February 1974, the site was ready for rig-up. Meanwhile, at Calgary, a subsea blowout preventer was being tested at actual anticipated operating temperatures. Westburn Engineering designed this subsea equipment to adapt to the conventional land rig. Anchored to surface casings cemented into the ocean floor, this would be an extra safety precaution, in addition to the surface blowout preventers, which would be located above ice level. A rig with several historic achievements was chosen to drill the well. Commonwealth High Tower Rig No. 2 had already drilled 15 wells, including 2 directional relief wells and 5 gas producers. The main factor in its selection, besides the experience and competence of its crew, was that Rig No. 2, though capable of handling the Hecla project, was relatively light. The rig was flown in by Hercules aircraft to an ice airstrip 1 mile from the drilling location where the moon pool awaited the rig-up activity. As complete darkness gradually gave way to the limited daylight of February, adaptation of the rig for the subsea equipment commenced. Rig-up began in mid-February, and 3 weeks later, Hecla N52 was ready to spud. Ready also was the diver shack, 500 feet from the moon pool on the ocean ice. From this shack, a team of divers from underwater specialists of Calgary would swim the 500 feet to the moon pool, pulling a strong, buoyant length of polypropylene rope. Though the divers never venture more than a few feet below the ice surface, the journey is still hazardous. No measure of security was overlooked as the underwater guidance equipment was checked and rechecked. The lead diver was fitted with a headband containing a sensitive antenna, plus watertight earphones and microphone inside a white capsule, so that he could maintain communication with the moon pool. About to begin, the divers were handed their battery-powered underwater scooter, or diver propulsion assist. Fitted to this scooter was a sonar receiver that would home in on a pinger located underwater at the moon pool. The dive got underway and proceeded without incident.
You can start watching for any light. I think you're probably getting within a couple hundred yards of the pole.
Once at the moon pool, the rope was attached to a steel cable and hauled back through to the dive shack. Next, a high-pressure hose was clamped to the cable and pulled to the dive shack. This hose would be tied to an outlet below the shear rams before the subsea blowout preventer was lowered to the ocean floor to serve as a kill line through which mud and cement could be pumped into the well in the event control was lost at surface. This was yet another safety precaution to maintain well control. Resting on the ice platform over the moon pool and supporting the rig floor and derrick was the substructure. It was specially equipped with a series of pulleys and winches to handle the cables which would guide the drill string to the ocean floor, 421 feet below the ice surface. First step in drilling from the ice platform was to establish a firm foundation on the ocean floor. This was done by threading two 40-foot lengths of 13 3/8-inch conductor pipe below the guide base and installing it in the moon pool. The conductor pipe would later be lowered into a 17.5-inch hole on the ocean floor. With conductor pipe and guide base in position at the moon pool, a hole opener was lowered and expanded to 17.5 inches. Water depth was 421 feet. And the distance from the rig floor to the ocean floor was 438 feet. Spud date was March 5th, 1974. The expanded bit then drilled the 17.5-inch hole 77 feet into the ocean floor. Using the drill string as a guide, the 13 3/8-inch conductor pipe and guide base were lowered on the heavy guide line cables to their final resting place. When the guide base was firmly seated, the hole opener was retracted and retrieved, leaving the guide lines attached to the ocean floor, ready to guide the next item into the well bore. The hole opener was then replaced with a standard 12 1/4-inch bit and fixed into position over the moon pool in the guide frame. The bit and drill string were lowered on the guide frame to the ocean floor. And the well was drilled to a point 975 feet below the rig floor.
This should be about bottom here.
The 12 1/4-inch bit was then retrieved. On the ice platform, the 9 5/8-inch surface casing was cleaned before making its descent into the 29-degree ocean water. The first length of surface casing was fitted with a bright red float shoe to which the guide frame was attached. The casing string was slowly lowered under the direction of the guide frame until the float shoe was in the well bore. A retrieval bridle secured the guide frame to a cable which would haul the frame to the surface. The guide frame was retrieved and the emergency kill line connected to the outlet below the subsea blowout preventer. The subsea blowout preventer contained blind shear rams. By either manual control from the rig platform or by hydraulic pressure contained within its 3 cylinders, the rams could shear the drill string and close off the well in the event of a blowout. The subsea blowout preventer was attached to the top of the 9 5/8-inch casing string and the entire assembly lowered on drill pipe to the ocean floor. A highly mobile underwater television camera observed the installation activities, eliminating the need for divers to work on the ocean floor. The subsea blowout preventer, stack, and television camera were taken down with the guide base, soon coming into view. The 9 5/8-inch surface casing was cemented in the well to a depth of 940 feet. An hydraulically controlled connector was then placed over the moon pool and attached to the first length of riser. The marine riser pipe was run and firmly secured to the subsea blowout preventer using the hydraulic connector. An hydraulic tensioning platform was attached to the marine riser. The tensioning platform would compensate for vertical ice movement due to tide fluctuations and maintain a constant positive tension on the riser to prevent buckling. Maximum tidal movement at Hecla was 1.5 feet. Vertical ice platform deflection was carefully checked daily to ensure the safety of the rig. During the drilling operations, the weight of the rig caused the ice to settle 6 inches. Maximum permissible deflection was 18 inches. A large all-terrain vehicle was used to transport surveyors between the rig and onshore triangulation stations. The distance from a fixed point on the platform to 2 land-based stations 9 miles away was measured daily using conventional microwave distance measuring equipment. This system enabled measurement to be made even under near-zero visibility conditions. The marine riser was designed to tolerate horizontal ice movement of as much as 20 feet. As it happened, the platform moved no more than 2 feet from its original position during the entire drilling operation. With the riser and constant tension apparatus in position at the rig, the final step before beginning conventional drilling operations was to install the surface blowout preventer, the first line of defense in the event of an accidental blowout. From this stage onward, conventional drilling methods were used. An 8 3/4 inch hole was drilled to 2,400 feet. 7-inch casing was landed in the wellhead at the ocean floor, and a 6 1/4 inch hole was then drilled to a final depth of 3,080 feet. The well was then evaluated by logging and drill stem testing. The open flow potential of the well was established at 52 million cubic feet per day. Hecla N52 found the crest of the structure 400 feet higher than the onshore wells, indicating an overall field length of at least 16 miles. Now all that remained was to seal the well before rigging down. The special abandonment procedure was designed using permanent bridge plugs in addition to normal cement plugs. A casing cutter was used to sever the 7-inch casing above the plugs. The 7-inch casing stub, casing hanger, and seal assembly were retrieved. A larger cutter was used to slice through the 9 5/8 inch surface casing and 13 3/8 inch conductor pipe 10 feet below the ocean floor. The abandonment was completed by April 15th, and rig number 2 moved to its next drilling location. With the retrieval of the subsea stack, the ocean floor was left completely free of any obstructions. By using a conventional rig, the cost of drilling Hecla N52 was $2 million, 1/4 of the estimated cost of drilling Arctic offshore wells by any other presently proposed system. These other proposed systems will involve an extremely high capital investment and cannot be made available for 4 or 5 years. Because of declining reserves in Canada, the early discovery of new oil and gas reserves, which are known to exist offshore in the Arctic islands, is of great importance. Panarctic's ability to economically drill offshore now will advance the date on which these reserves can be brought to market. The Panarctic method of drilling from a stable ice platform has proven to be a safe and practical solution to offshore drilling. And so the story ends. Hecla N52, a successful pioneering approach to offshore oil and gas exploration in the Canadian Arctic islands.